Hi, I'm Praneet Singh, a graduate student in the EC department of Purdue University. Today, I'll be presenting my paper, Animal Localization and Camera Trap Images with Complex Backgrounds. This work was done under the guidance of Professor Amy Reibman and Professor Maggie Ju. I'd also like to thank Professor Stacy Lindshield from the Anthropology Department for supporting this work. So this is a basic overview of my presentation. I'd first introduce the topic, then I'll talk about some of the challenges faced in the camera trap domain. I'll then introduce our dataset and our proposed system. I will then talk about some of the experiments that we conducted and the results that we obtained. Finally, I'd like to conclude and talk about some of the future work that is possible. So, camera traps help monitor animals in their natural habitats in a non-intrusive manner. We can obtain key insights on animal health and population densities by analyzing these images. However, camera trap images tend to have complex backgrounds. As a result, even accurate analytics using state-of-the-art learning-based methods becomes difficult. So in this paper, we propose a system based on robust principal component analysis that helps spatially localize animals in complex background camera trap images. Now, I'll talk about some of the challenges that are faced in the camera trap domain. The datasets in this domain tend to have a large number of false positives in empty images. This is because camera traps are motion sensitive and collect images in the form of bursts. As a result, animals passing behind the camera trap, moving vegetation all trigger the camera trap. Sometimes camera traps capture images once the animal has already exited the scene. Animals being too close or too far away from the camera trap also render unusable images. The datasets in this domain also tend to be extremely diverse from one another. Different regions of the world have different species and different backgrounds. The datasets also tend to have a heavy bias towards one particular class of species, again depending on the region in which they were captured. Now talking about our dataset, our images were captured in the Niokolo-Koba National Park of the Senegal region. 17 distinct animal species have been captured. Out of the 1,500 images that were captured from two different locations, 3 of them are empty and 500 of them contain baboons. In comparison to two of the popular datasets in this domain, Snapshot Serengeti and Caltech Camera Trap, our dataset has extremely complex backgrounds. Now this slide shows the comparison between our Senegal dataset and the popular datasets. As you can see from the first two rows, the popular datasets have relatively simple backgrounds and the animals are very distinct. However, coming to our dataset, you can see dense vegetations and shadows are very common. Now this slide shows us some of the other difficult scenarios that are very common in our dataset. As seen from the first two images, there is a rapid illumination shift that is seen in the same scene when it is captured just a few hours apart. We can see animals being occluded by the dense vegetation, animals camouflaging in the environment, and only parts of animals being captured by the camera trap, and these scenarios are really common in our dataset. Now this slide shows the block diagram of our entire system. Robust PCA is the most integral part. We propose that robust PCA performance can be improved by providing it with better camera trap image stacks. What do I mean by better? By better, I mean camera trap stacks that have more images with similar illumination and color content. We use an animal presence classifier and a clustering block to basically create these camera trap stacks. After this, robust PCA creates the saliency maps and the final animal localizations. But how did we get this idea? So first, I'd like to go over an overview of robust PCA. Robust PCA operates on a stack of images of frames. It then iteratively solves a convex program called Principal Component Pursuit that splits the stack of images into a sparse and a low rank matrix. The low rank matrix contains the background entities, while the sparse matrix contains the foreground objects and noise. On reviewing some of the work done in this domain, we see that robust PCA performs exceptionally well in the background-foreground separation task when it is evaluated on videos. This is because videos contain a large number of frames with similar content in them. However, when it was applied on camera trap images, its performance suffered. This is due to the bursty nature of camera trap sequences. They contain about 3 animal images taken over a duration of 15 seconds. This isn't enough for robust PCA to successfully separate the background from the foreground. As a result, we decided to create better camera trap stacks with more images of similar illumination and color content. Although pre-processing techniques have shown to improve the performance of robust PCA, no quantitative evaluation was done on this. In terms of analytics, deep learning models have been applied to the popular camera trap datasets, and their performance has been really good in terms of animal detection, classification, and counting. However, no images with complex backgrounds were considered. Now, I will go through each block of our system and explain it in detail. The animal presence classifier is extremely essential in our system because of the inherent property of camera trap datasets that they have a lot of empty and false positive images. In our case, the empty images are leveraged to assist robust PCA in background-foreground separation. We tested different deep neural network architectures as animal presence classifiers, and these are the results that we obtained. We saw that VGG16 performed the best and gave us a testing accuracy of 96%. Now, coming to the clustering block, this block is very important because we cannot just append empty background images to camera trap sequences. There needs to be some similarity in terms of illumination and color content. So we pass the empty images through a deep neural network, extract dense features, and subject it to k-means clustering. The cluster background images are then appended to the camera trap sequences based on finding the closest cluster center to each sequence. This slide shows us the results that we obtained from the clustering block. As we can see from the first three rows, that the clustering block did a great job on separating images based on the illumination content. From the last two rows, we can also see that it did a good job in separating images based on the color content. These rows also show a good distribution of all the types of images that are present in our camera trap dataset. Now, we've created the better camera trap sequences by appending the background images to the existing camera trap stacks. We then pre-process these stacks by using Gaussian blurring, histogram equalization, and local binary pattern. We then run robust PCA on the pre-processed image stacks, and finally apply post-processing techniques like thresholding and morphological operations on the sparse matrix obtained. This gives us a saliency map and the final animal localizations. This slide shows us how the localization is achieved by our system. Here I've considered only one image from an entire camera trap sequence. This image goes through pre-processing and robust PCA to get the sparse image. We then post-process it to get the saliency map and then use contouring to generate the final animal localization. We now had to evaluate how our better camera trap sequences help improve the performance of robust PCA. We also wanted to see if robust PCA's performance improved under different illumination conditions and camera trap sequences of different sizes. So the illumination conditions considered were strong illuminations, weak illumination sequences, and also night and twilight sequences. The different stack sizes that were considered were 3, 9, and 15. Then we evaluated the performance of robust PCA under two conditions. One, where the camera trap stacks had only animal images, and second, where the camera trap stacks had both animal images appended with similar background images. This slide shows some of the camera trap sequences of size 3 that were considered. As we can see from the first two rows, the sequences are very similar to the results of the clustering block. We also saw some night and twilight camera trap sequences that were considered. Now coming to the results that we obtained, all the results have been expressed as an intersection over union between the final localizations that our system gave us and the manually annotated ground truth bounding boxes. We see a 12.5 increase in IOU when we use our better camera trap sequences with background images. From the results, we can also see that robust PCA starts performing better for camera trap sequences of smaller sizes. This is because, thanks to the appended images, it now has a clearer picture of the background. We also see that robust PCA starts performing better when camera trap sequences involving strong illumination conditions were considered. Because our system generates a saliency map, we wanted to evaluate its performance against a state-of-the-art deep learning-based saliency detector called R3net. R3net was pre-trained on the MSR10K dataset, which has complex background images with animals in them. The same post-processing was applied on both saliency maps to generate the final localizations. As we can see from the final results, our IOU seems to be consistent at around 60. However, R3net tends to fluctuate in this case. Although R3net does beat our system in some of the illumination conditions, under strong illumination conditions, our system always outperforms it. This slide again compares our system's results to R3net's results. The first column shows the ground truth bounding boxes. In the second column, we see the R3net's localization. We see R3net allows a lot of background objects to seep into the foreground, and also it does not capture all the species in the image. However, in terms of our results, we see that all species are captured and also no background objects seep into the foreground. Finally, I'd like to conclude by saying that we've created a system that helps create more suitable camera trap sequences that help improve robust PCA performance. Using our system, robust PCA starts to perform better for camera trap sequences of all sizes and under all illumination conditions. Our system outperforms R3net, a learning-based saliency detector. In the future, we would like to explore how these localizations can serve as an attention mechanism for learning-based methods. When we use deep neural networks, they tend to learn a lot of noisy features when complex background images are involved. Using our localizations, we can ensure that these deep neural networks learn features from only the important parts of the image. Thank you, and now I'll take questions.